Hey everyone, hope you guys are doing well. Hope you guys enjoyed yesterday to either catch up with your work or just have a day off. We're going to make some progress with chapter 2. I want to review a little bit with the homework yesterday from 2.1, finish up a few things with 2.1, and then we'll go into 2.2 with power rule. Let's see here. All right, so this was the homework from Tuesday, and then yesterday morning I spent time going over this and then I recorded it. So let me know if you do not have access to the calculus help session channel or Teams page that I created. I made a new Teams page. I wanted all my students to be able to access it if I record it, and I won't have to put it in every period's team page. So yeah, so send me a text remind if for some reason you're not able to see this the calculus help sessions page. But I went over the homework yesterday during that time, and I just want to highlight a few things from that session. First is that this limit definition of a derivative is really coming just from slope, right? This is just a fancy notation for slope. It looks a little messy because we don't have numbers. We're using variables, but the idea is that we're taking 2 points because we're taking the same function. We're just extending that x value to be a different value so that we're forcing 2 order pairs out of it, because that's what we start with, right? With slope formula, we always start with 2 order pairs, and then we find the slope. But along that process, we're also allowing for that second point to move. We're decreasing that distance for h, and what's going to happen is that second point is going to kind of fall into that first point. And when it does, through that limit process, then we're able to achieve slope using just 1 point, because that second point has disappeared into that first point. But the idea remains the same, and it's the fact that derivative comes from the slope formula, which means that derivative is basically just another word for slope, just another, but it's now has more ability, it has more flexibility to find slope of any point on the curve, and it's not restricted to just a straight line. So when we go through this process of replacing, getting our function so that we can make the appropriate expression for f of x plus h, right? So the process that I went through that helps some students is forcing parentheses around all the places where x's were, and then once you get those open parentheses, you know exactly where your x plus h is going to go, and that will decrease the chances of making a mistake if you're putting restrictions in place. Kind of forces you to put that x plus h within the correct locations. So once we get that numerator to be out of function notation into values that we can actually work with, and we subtract the f of x, the original function, make sure parentheses in place. Clean up, combine like terms, all the non-h terms will go away, and we're only left with terms that have h's in it. We factor the h out, reduce, reevaluate, and what we get back in return is the slope formula for this function, for this original function. So 2x squared minus 3x plus 1 is just a shape of a parabola. But now we have something that can give us additional information about this curve. We know, I mean, we still have a function that will tell us order pairs, will tell us the location. But now with the slope formula, we can gather information about the steepness of any point on the curve. So if I give it an x value of -3, I can plug that -3 in for x, and then I get a number back in return, and that number is going to correlate with the steepness of that point on the curve. And I can do that with any points on this curve by putting it into the derivative formula. So this is my slope formula for my original function f of x. So that's what the limit definition does for us. I skipped over this alternate definition, this concept, but let me just kind of go through it real quick. The alternate definition does a similar thing with the limit definition, the general definition. They both give us information about slope of the graph. But the difference is that the general definition will take you to the slope formula. And then if you want to find the slope value, you'll have to take a second step. And that second step, you can choose which x value to plug in, and then that will get you to a numeric slope value. But the alternate definition is going to bypass the slope formula, and it's going to move you directly to a number, and that number is the slope value. So we don't see this as often. Sometimes it's shown up on the AP exam, but I'm mainly going to skip over this, and then if we need to, we'll come back and revisit this. But the nice thing about the alternate definition is that visually, you're more convinced that this is related to slope, right? Because this does look like the slope formula, more so than this one, right? Because you have the y2 minus y1 over x2 minus x1. You got the limit process attached to this, meaning that we're taking 2 points and we're moving those 2 points closer towards each other until the only thing left is a point, and then we're basically able to find the slope at a point. But this process will just bring us to a number, and that number is the slope value. Okay, so using the limit definition of a derivative, for number 3, we go through the same process, get the parentheses in place, put the x plus h. But we see we have a bunch of radicals in the numerator. We know we're still trying to find an h to cancel out. But the process that we learned with the first unit was we can multiply by the conjugate. So if we multiply by the conjugate, we can get that numerator to clean up a little bit, get the h's to cancel out, reevaluate, and then we get down to an expression, and that expression is the slope formula for this original graph. Number 4, same idea in the sense that we're finding the derivative. But actually, this went a little further. This is finding the slope at a point. So after we find the derivative, we're going to be plugging 3 into the derivative function. But first thing first, we get our parentheses to show up. We replace those empty spaces in the parentheses with x plus h. And now we have something that we can use to replace our f of x plus h. We have 2 fractions. We got a fraction within a fraction. We want to try to get this down to 1 fraction by first finding common denominators. Get that to clean up. Once it's down to 1 fraction, we're going to have an easier time identifying how the h's will cancel out. Once the h's goes away, we reevaluate, we get to our derivative. And then one final step is we can find f prime of 3. So f prime of 3, let me put this up here. It's just us putting the 3 into my slope formula. So 2 over 4 is 1/2. Okay, so again, what this tells us is that whatever this graph looks like, when we reach a value of x equals 3, this graph is going to exhibit a positive slope that's very gradual. It's barely rising, but it's going to be a slope of 1/2 at that point. Number 5, we had to find the derivative, find the ordered pair, find the slope, because we're after the tangent line equation. Okay. The initial process is the same. We find the derivative through our general definition, and we arrive at our slope formula, our derivative function. So I'm putting the function and derivative next to each other because I want us to understand the distinction between a function and a derivative. The earlier you understand this, the earlier you can visualize what information this is giving us, the easier things will be down the road, because we're going to see this a lot where they're going to be pairing information about the function and the derivative, and we need to keep clear in our heads what information each of these functions are providing for us. So a function is basically just going to give us information about ordered pairs. Okay. If I give an x value, in return, it's going to give me a y value. Likewise, if I'm looking for a specific y value on the graph, I can put that y value into this location or this portion of the equation and then work backwards and solve for x. So I can give an x, find the y, or I can give a y and find the x. Okay, so works both ways. Slope, the derivative function is similar. Okay, it will take an x value. If we give it an x value, we also get a number, but the number is not the same as the number that we get here. Right? The number that we get here is the physical location. The number we get here is the slope at that location. It's the steepness at that location. So if I give it an x value, I get a number. That number is a slope. Likewise, we can do the other way around. Maybe you're looking at, maybe you have a derivative function and you're looking for a specific slope. Maybe you're saying, I want to know on the graph, where is there a slope of 10? Then we can do is we can plug 10 into the slope portion of the formula and then work backwards and solve for x. When we solve for x, we're able to locate where on the graph is there a slope of 10 or a slope of 9 or whatever slope you're looking for, you can put into this location. Okay. So for this particular problem, we plug -1n into the function and we get the location, the y value, -1, -5. So that's the ordered pair that we're after. But we're also after the steepness at that point. So we'll take -1, put it into the derivative function. In return, we get the slope. So we know that at this point, the graph is going to exhibit a steepness of +8. Once we have our ordered pair and our slope, we put it into our slope formula, our point slope form. X1, Y1 gets replaced with -1, -5. M gets replaced with 8. So this is our equation. I'm not going to ask you to graph, but I want to make sure that I can connect any abstractness with something visual, something more concrete. So this is what the graph looks like. This is what the parabola is, the 2x minus 3x squared. There's my ordered pair, -1, -5. The steepness, the tangent line, is +8. So when I extend that line into a dotted line, this is what we found. We have the ordered pair, we have the slope, we put it into point slope form, and now this equation describes this line that I drew here. All right, any questions that you guys have about this process, about the conceptual understanding of this? Because we're really going to be building on this for the rest of the semester and the year too. We're going to see this come back over and over again. So if we're having trouble with this, I want to know, because I don't mind spending more time on this, because if we're having trouble here, things are just going to get, I mean, we're just building on this foundation here, this concept here. Yes, question, Jason?
Yeah, I'm kind of confused right now on like which is like how to do both. Like I kind of zoned out for a bit and now I'm just kind of confused. I've been trying to pay attention to catch up, but I don't really know.
Yeah, tell me where you're.
On the slope value like function.
Got it. Okay, so this is my slope formula. Does this process make sense going all the way down to this f prime?
A little.
A little bit.
I
Okay,
think I'll figure it
so
out more. So
we're using this limit definition here. We're plugging x plus h in. We're going through and cleaning up, canceling out, and we're getting it all the way down to the derivative. Okay, we're gonna have a much faster process of going through this, but right now I was just focusing on the fact that a derivative and function, they both describe the same curve, but they give different informations about the curve.
okay.
So one will give us the ordered pair, and the other one will give us the steepness of the point on the curve. It'll tell us how steep that point is in relation to the curve. Yeah. So, this process we're going to kind of let this phase out a little bit, because this is the importance of this is just to see the connection that anytime you see the word derivative, I just want you to visualize slope. And this kind of helps us see that we're just building off of the slope formula, adapting it so that we can have a much more robust slope formula with the derivative.
Okay.
Okay, good. Any other questions that you guys have? All right, we're really going to be building on this. We're going to be able to get from our function to a derivative a lot faster now. We have a much better process, a much efficient process of going through. So let's look at some of that. So today's notes. Give me a moment to find it. All right, so derivative rules. The first one that we're going to come across are these constant and power rule. Okay. Okay, so here's the big idea here. Constant rule. If our function is a constant, then our derivative is always going to be 0. Right, so rather than memorizing this, I want to create a visual picture of this for you. Okay, so let's say we have a function f of x equals 5, which is the same thing as y equals 5, right? And we know that y equals 5 is just a horizontal line. So there's y equals 5. What is the slope of this line here?
0.
0, right? Imagine yourself walking along the path of this line. You're not going to experience any steepness, right? Steepness is 0. So slope, steepness is 0. So if our slope is 0, then our derivative is also 0, because derivative is just slope. But it's the same slope no matter where I am on this line. So any constant that I have, my derivative is always 0, because if you visualize drawing a constant horizontal line, you're always going to experience a steepness or slope of 0. Okay, so any constant, my derivative is just equal to 0, because derivative is the same thing as slope. Now, let's do it to power rule. So this is going to be probably the derivative rule that you come across the most for our course, right? So this is kind of the foundation that we're building a lot of things on, the more comfortable that we get with power rule, the better things will be as we put things on top of it. Okay. So power rule, these are powers of a variable. So if I have a function that's in the form of x to the nth power, we can quickly find the derivative by doing this. So f becomes f prime because we have our notation there. And then here's our derivative process. We bring that exponent down in front, and then we subtract 1 from that exponent. A lot faster, a lot more efficient than having to go through f of x plus h, getting it in, cleaning up our numerator, canceling out, factoring, canceling out, reducing, reevaluating. Now we have a much more efficient process. So the steps that we're going to do, let me put that in words here. We're going to bring that exponent down in front of the variable. We're going to multiply that as a multiplication relationship there. Bring that variable down in front, multiply. Next thing, we're going to subtract 1 from that original exponent value. So this n, we got to subtract 1, so n minus 1. So as often as you're going to be using power rule, we have to make sure that that we work within the conditions that are required for power rule. Sometimes the issue with power rule is we sometimes do it when it's not in the correct form. Okay, so if it's not in the correct form, if it's not in the correct place, we may do power rule that is not really representing the derivative or not representing the slope formula. So we need to make sure that all of our conditions are met. Before we apply power rule. So here are the conditions here. Let me number them. I left one of them off. So if you guys can number 1, 2, and 3. So the first one is we need to convert radicals to rational exponents. So this is what I mean by that. If I see square root of x, I want to rewrite that as x to the 1/2. If I see cube root of x, I want to rewrite that as x to the 1/3. If I see square root of x to the 7th, I want to rewrite that as x to the 7/2. If I see the cube root of x to the 4th, I want to rewrite that as x to the 4/3. Okay, so I just want to give a lot of variations here so we know how to convert radicals to rationals. And the reason why we do that is because if we can see a numeric value here, we're going to have a much easier time deciding what we can bring down in front and what the result of subtracting that exponent is going to be. Second thing is we need to make sure that all the variables are in the numerator position for us to be able to apply a power rule. Okay. A variable in the denominator doesn't mean the same thing as a variable in the numerator. So that means a variable in the denominator is going to have a much different shaped graph than a derivative than a variable in the numerator. So we can't just go about applying power rule if the variable is out of place. So this rule is only meant for numerator. So this power rule, this derivative rule, doesn't apply if it's in the denominator. Okay. So we have to move variables from denominator to numerator. And usually the way we do that is we force the variable to change locations, but to do that, a lot of times we're changing the sign of the exponent. Changing the sign of the exponent. Okay, we'll look at some examples of that. So the third condition is we need to expand all of our terms. So what needs to happen is we need to make sure we resolve all of our parentheses. If there's one of them that we are not able to resolve, then we can apply a power rule. Okay, so sometimes we're not able to move the variable from denominator to numerator because it's not going to make the problem any easier for us to do. Sometimes we're not able to resolve parentheses. So we need to recognize that, because if we can't resolve parentheses, then that's an indication that we need to explore another avenue. We're not able to apply power rule in the present state that it's in. All right, so recognizing what needs to happen for power rule, but then also recognizing down the road when we can do power rule and when we're not able to, and it's all dependent on can we get these to clear. Okay. Okay, so let's start with the easier example, and then we'll move towards just more involved steps. Let's start off with y equals x to the 7th. Let's see if it passes all of our conditions here. So radicals to rationals. Okay, there's no radicals to worry about. Looks like we're good there. Variable from denominator to numerator. There's no denominator variable, so we're good there as well. Expand all terms, no parentheses, so all three conditions are good. We're clear to apply power rule. So f becomes f prime, much the same way we'll apply that with our variable y. So y becomes y prime. And now we can apply power rule for x to the 7th. So we're going to take that 7, sitting in the exponent location. We're going to move it down in front. So it becomes 7x. And then we're always going to subtract 1 from the exponent. So 7 minus 1 is 6. So here is our derivative function. And again, derivative function is just a slope formula for this graph. So whatever this graph looks like, we can find the steepness behavior of any point on this curve by using this formula. Right. Much faster, right, than having to go through the limit definition. Any questions here? All right, part B, g of x equals q root of x. We want to find the slope formula, the derivative function for g of x. Let's go down our conditions here. Do you see any that we need to resolve?
We need to change the root.
Yeah, this radical is not in the best optimal state for our power rule. So let's convert it. So cube root of x is just going to be x to the 1/3, right? So as a side note, anytime you see a radical, a lot of times you're going to see some missing numbers. So anytime you don't see a number to the right of a variable, that there's a hidden exponent of 1. And we always write it as x to the, whatever number is to the right will go in the numerator of the exponent. Whatever number is in the root position will go in the denominator of our exponent. And that is why, as a side note here, if I have square root of x, square root of x is really, there's some numbers that are hiding, right? The number to the right that's hiding is a 1. The root, there's a hidden number of 2. So that's why we write this as x to the 1/2. So I think a lot of times we just memorize square root of x, x to the 1/2, but it's because there's a 1 there, there's a 2 there, and we write it as exponent over the root. Okay, so back to this problem here. Let's check the other conditions. Denominator to numerator, so there's no issues with the denominator. It looks like we're good. Expand all terms, there's no parentheses, so I think the one issue that we had, we resolved it, so now we're ready for power rule. So we apply power rule. Bring the 1/3 down in front. And now we're going to subtract 1 from the exponent, right? Before we did 7 minus 1, but now it's going to be 1/3 minus 1. Now 1/3 minus 1, we're dealing with a fraction here, so I'm going to force that 1 to be a common denominator so that I can easily subtract those fractions. So 1/3 minus 1 is the same thing as 1/3 minus 3/3, but I'm forcing a common denominator to make it easier for me to subtract these fractions. So if my denominator matches, I can then subtract those numbers I see up top. So 1 minus 3 is -2. Okay, so there's my derivative. This formula will tell me the steepness of any point on this curve. Right, now, once you find the derivative, I am going to ask you to do a little bit of cleanup. And what I mean by cleanup is I want positive exponents in the answer. So if you have negative exponents left over, you're going to take that variable that negative exponent is affecting and push it down to the denominator so we can make that into a positive exponent. So when this x gets pushed down, it's going to share the same space as the 3, and now we can clean that negative exponent to a positive exponent. Okay, any questions with this process here?
Can you clarify how you went from g of x to g prime?
Sure. So g of x to g prime, we are applying this this power rule here, this derivative rule here. So we're going to bring the exponent down in front of the variable. So that 1/3 comes down in front. And then we're going to subtract 1 from that original exponent value. So that becomes 1/3 minus 1. But if I'm doing 1/3 minus 1, I don't have common denominator. So I'm forcing that minus 1 to be a 3/3 to match this denominator. That way I can do 1 minus 3 is -2 and becomes -2/3. That answer your question?
Yes, thank you.
Okay, thanks. All right, anything else with B? Part C, 4 over x to the 5th. We want to find the derivative, but let's go and check. Do we have any issues that we need to resolve? What do you guys think?
There's a variable in the denominator.
Yeah, this is not suitable for power rule. So that x has to come up, right? Variable in the denominator is not a location we can use for power rule. We have other rules later on that can handle. If we want to leave that in denominator, we can do another. There are other rules that we're going to learn about. But if we want to do power rule, we got to make sure every time our conditions are all met. So that variable is going to have to come up. If we force a variable to the top, we're going to have to change that exponent to make it to balance. So these are the same expressions. It's just that this is more suitable for the next step that we want to take with power rule. So here's power rule. Oh, let me double check here. No radicals to worry about, right? No expansion, no parentheses. So there's only one issue, and we took care of that one issue. Okay, so again, we apply power rule. Bring the exponent down. So that exponent comes down. Notice that there is a number there already. So when that exponent comes down, it's going to end up multiplying with this number in front. And then just like before, I'm going to subtract 1. So when I see whole numbers, I'm just going to put a -1. But when I see a fraction, I'm just going to put, I'm going to match the denominator. Just visually, it's easier to quickly subtract fractions if I can get that denominator to match. Okay, so -5 minus 1 is -6. So we have a derivative. Let's just do a little bit of cleanup. -5 times 4 is -20. I still want to resolve that negative exponent, so I'm going to push that x to the bottom to get that negative to become a positive exponent. Okay, questions so far? Okay, part D. This looks more complicated because we have multiple terms, but notice that there are no parentheses in the way, so we can really treat each like a separate problem. We'll treat each term as a separate power rule problem. So we're going to find the derivative of each, but every term we'll treat like these are 4 separate problems. We'll find the derivative of each, and once we do that, we'll just merge them together and put all the results next to each other. But the way that I am going to have us make these connected is that some terms are more ready than others to jump into the derivative step, into power rule. But we're going to force every term to wait until everything is ready to go. Then we can do all the derivatives all at once, rather than take the derivative of one, clean up the other, take the derivative of one, clean up the other. If we mix the methods for each term, it's easy to lose track. If we lose track, then it's hard to go back and double check your work, and sometimes you end up taking the derivative twice because you thought you've cleaned up when you've actually taken the derivative once already. So we're going to examine each term, and if it's ready, we're going to put it down the same. If it's not ready, we're going to make that adjustment. We'll make sure every term is ready to go, and then we jump for the derivative all at once for all the terms. Okay, so first term, 8x to the 2/3. Do we see any issues that we need to adjust, or is it ready to go?
It's ready to go.
Ready to go. Okay. No radicals to move, no variable to adjust, no parentheses. Okay, so if we're ready to go, we're not going to find the derivative yet, though. We're going to wait till every term is ready. So we're just going to copy that down. Okay, what about second term? Do we see any issues there?
We have to convert the radical.
Yeah, convert the radical, right? There is a hidden number there, which is a 1. So fifth root of x is just going to be x to the 1/5. I think that's the only issue we have. No parentheses, no denominator, so we can move on to the next term. All right. Any issues here?
There's 2.
Yeah, there's 2 issues, right? So which one would you fix first?
The denominator.
Yeah, let's get that number to show up, right? Let's get this x to the 1/2 to show up. So I'm going to rewrite this as 2 over x to the 1/2. So we took care of the radical issue. So what's the next one that we need to take care of?
I'll move it out of the denominator.
Yeah, it's got to be in the right location. So let's push it up. Now, anytime you move your variable around, you got to adjust with your exponent so that my exponent is going to change to a negative here. Okay, any questions from here to here to here? No derivative. All we're doing is we're just putting it into the form so that power rule can be applied to the term. Any adjustments here? Constant will just stay, right? Okay. Every term is ready for power rule, or every term is ready for its derivative rule. So we're going to jump to y prime. So power rule, bring the exponent down in front. Subtract 1 from the exponent, so minus 3 over 3. Second term, bring the exponent down in front. Subtract 1 from the exponent. Bring the exponent down in front. Subtract 1. And what's going to happen to 0.875?
0.
Good, right? A constant is just a horizontal line. And a horizontal line has a slope of 0. So we'll just do a little bit of a different process for constants, visualizing it as just a flat line, and that line has no steepness, so slope 0. So it goes away, but I'll just put a 0 just to show that the result of each term. So we have our derivative. Okay. Let me just do a little bit of cleanup. Okay, just give me a minute to finish this problem here. I'm going to multiply the top numbers together, so 16 over 3. This variable is out of place for my cleanup. I don't want negative exponents. I'm going to push this variable to the bottom. So when it comes down to the bottom, it's going to share the same space as that 3. So I can force a positive exponent in my answer. Same thing. This x to the negative 4/5, I want to resolve that negative exponent, so I'm gonna push that x to the bottom. One half times 2 is just 1. Push this x to the bottom. And then the 0 goes away. So here's my slope formula for whatever this graph looks like. Okay, your homework is, I have that indicated on your, under today's date. It's just the odd number problems. I spelled out the condition, the derivative power rule, and the key is attached. So you can work through and you can check your answer along the way. Tomorrow morning in the calculus help session, I will go through this worksheet or this homework. I will record it, so you don't have to be there live. You can just you can watch it if there's any questions that you have. But yeah, if you're not on the help session channel, let me know, and I will add you to that Teams page. Okay, thanks everyone. Hope you guys have a great day. See you tomorrow.
Thank you,
Have a nice
Mr.
day,
Yang.
Mr. Yang.
Thank you. See you guys.
Bye. Thank you.
Bye. Have a good day.
Thank you.
Bye.
Thank you, Mr. Yang.
Thanks. See you tomorrow.